Hello, everyone. Good evening. Hope you're having a nice summer. Great. So, welcome to the methodology seminar from the Center for Transportation and Logistics. I'm Devjit Roy. I'm a co-chair of the center, and I'm also co-chaired by Professor Sandeep Chakrabarti. He'll join us very soon. This is one of our effort to our capacity building in India in general. As you would realize in India, especially logistics on the growth, right? There is so many sources of technologies, whether it is blockchain, IoT, whether it is movement of goods in the trucks or the airports or as well as the ports. So I think there is this huge opportunity to collect real-time data today. So as we are collecting gazillions of data points, how can we really leverage? That is not very clear yet in our domain of transportation logistics. So here we had a golden opportunity because we had with us Professor Samrat Roy. He joined our faculty in the operations and decision sciences area recently, and we thought that, well, he will be a perfect fit to address this question. So Professor Samrat Roy's expertise is in statistical models. Particularly, he works on high-dimensional data, tensor models, among many, many others. Before going to academia, rather than doing PhD, he also had a stint with Credit Suisse and one more bank.
Ernst & Young.
Ernst & Young, right. And post that, he also did his PhD at University of Florida, and then he had also a postdoctoral experience at the Wharton School, where he was associated with the Data Science Center. So without too much of taking time from him, I would give the floor and the Zoom both to him today, because a lot of participants have joined online. I would say probably about maybe 100, but and he's very generous with his time. He told once he'll finish up the presentation, he's also willing to take a lot of Q&As. So have your questions ready, and we will just get started. Yeah. So without delay, the floor is to you. Thanks.
Can you hear this? Can you hear me? Okay. Firstly, thanks, Professor Devjit, for the nice introduction, and hello everyone. Thank you so much for joining both online and offline. As you can see, today's discussion is on recent machine learning and data science applications in transportation and logistics. So what I'll do is I'll start the discussion with a very true story. Okay. A few days back, while I was preparing all these slides, I had a phone chat with one of my very close school-going teenage nephew. And I told him that, hey, I am preparing all these slides for one of my talk, and I'm reading and learning about the tools and techniques to predict the package delivery time. I just gave an example. So the moment I said that, surprisingly, he was like very excited. And he asked me this question. Oh, you are reading about all these things. Then can you please tell me what exactly, when exactly my PS5, that means the PlayStation, will be delivered? My dad has ordered it for me, so that I can enjoy it during my summer vacation. But the delivery is getting delayed and delayed again and again. So, of course, I was not expecting this kind of question from him, right, from a school-going boy. So I mumbled for a moment, and then I said that, well, people are using a lot of AI and ML tools to predict the package delivery time and so on. And then what he said was very significant. The moment I said this, the next thing he said is, well, you are saying AI and ML, then should I ask ChatGPT about this? Will ChatGPT be able to tell when my package will be delivered? So for me, this particular question is the biggest reason or the biggest motivation behind why we as a researcher should talk more and more about the AI and ML tools. See, any chatbot, for example, ChatGPT, Gemini, or anything, they can tell us how to do. If you know what to do, they can tell us how to do. But we as a researcher or as a practitioner, we need to decide what to do, why to do, and when to do. These 3W you need to decide. Then ChatGPT will come into the picture. So this is the biggest motivation at this stage, because if we have to use ChatGPT, we first need to understand, at least a little bit understanding is required on the methods. Okay, not very detailed, but little bit. So with this motivation, let me jump into the literature review. So by literature review, what I mean is the state-of-the-art machine learning methods that have been used in transportation and logistics. For that, what I have done is I have categorized this whole transportation and logistic problems broadly, not all inclusive, broadly into 6 categories. So arrival time prediction, demand forecasting, then industrial process optimization, then comes traffic flow and location prediction, then of course vehicle routing problem, and the last one is anomaly detection. Now, considering these 6 broad categories in mind, this figure, this is the percentage distribution of the topic-wise and the machine learning technique-wise figures. Okay, so for example, this ML, this stands for traditional machine learning methods. This boosting and bagging, as I think some of you know, these are some ensemble techniques. So I'll come to that later. This DL is deep learning, and statistical is pure statistical, traditional statistical methods. And genetic is something called genetic programming, which is coming slowly nowadays. So as you can see, for some of the problems, for example, this genetic programming, these have been used only so far, have been used mostly for demand forecasting and for vehicle routing problems. So this is comparatively less used. And for example, for deep learning, as you can see, this industrial process optimization have been using this DL a lot. Okay, so now, of course, this is just 1 hour webinar, and we cannot discuss all the methods, right? So for today's discussion, what we'll do is we'll focus on these 2 things: arrival time prediction and demand forecasting. Okay, so let's start with arrival time prediction. Okay, so what I'll do is I'll start with this very first paper by Pani's 2014 paper. And what was their objective? Their objective was this. The objective was to predict the delay in arrival, okay, delay in arrival of ships in port with greater accuracy. Delay. Now, why this is important? As some of us already know, of course, I mean, most of us already know, because this arrival of vessels in a port has direct and indirect effect on many factors. For example, berth allocation problem, resource assignment, stowage planning, container stacking problem, and so on, right? So even a small amount of error in predicting the delay can like mess up with everything, like can disturb all the mechanism. So it's very crucial to predict the delay in arrival or the arrival time in general as correctly as possible. So even if you can offer a little bit more accuracy, then it's of high use, right? So with this objective and with this motivation, what they proposed, or what they rather used, is this one, this CART. I think some of you already know CART means classification and regression tree. I will discuss it very briefly. Now, before that, what is the response variable? Or by response variable, what I mean is what is they want to predict. They want to predict the delay in arrival, right? So delay in arrival, it's very easy to calculate. What is delay in arrival? Delay in minutes. It is just the time difference between the ETA, that is the estimated time of arrival that was notified, minus the actual time of arrival. This is the response variable they want to predict. And what are the predictors they used? Again, that was their decision. They used these many predictors. What are they? Length in meter of the vessel, okay, length in meter of the vessel, and that has some connection with the time taken for operations in the previous port, right? And also this length has something to do with the navigation time. So length is an important predictor, okay? Then ETS, estimated time of arrivals, ETA day, which day of the week the ship is supposed to arrive, ETA day, and ETA shift, which time of the day the ship is supposed to arrive, ETA day and shift. And vector type. Vector type, we can have 2 types of vessel, mother vessel or feeder vessel. This is one of the predicted variable. And then sailing status, whether the ship already departed the previous port or not. If it has already departed, then sailing status is 1, otherwise it is 0. So with all these predictors, what I have already told, they have used something called CART, classification and regression tree. Now, again, some of you already may know it, but what is this? This is very easy. So CART is a very simple, okay, very simple machine learning tools or technique, which is used to create this kind of tree-like structure, where the first step is to find the most suitable predictor variable or the most suitable feature based on which you will create this first node. Okay, for example, here ETA day is that most suitable predictor variable based on which we have created, actually the machine has created the first node. Okay, and then the next step is find the most suitable cutoff point to split that node. See, here the machine has chosen this particular cutoff. So 5 days of the week, that means Monday to Friday, that has been used for first node, and weekend, Saturday and Sunday, that has been used for the second node. Okay, these are the two main steps for a cart, and that's all. You just go on like this. You decide a variable which is used to prepare the node, and then you choose a suitable cutoff to split that node, and you go on like this. Okay, that's basically classification. And well, this is for regression purpose, but we can do the same thing for classification purpose as well. That's in general the structure of the decision tree. Now, first thing is where machine learning is coming into this picture. Okay, so we need to decide this, right? We need to decide the most suitable variable based on which we'll create our node. That's where machine has the role. Okay, machine will do some maths, which I'll not go into the detail of it. Machine will do some math and will choose for each node, will choose the most eligible variable based on which it will create the node. And also it will choose this suitable cutoff. These are the two primary roles of the machines. Okay, you feed your data to machine, and machine will tell you based on some maths, which I'll not cover today, that how to do it. Okay, now other common sense is the tree cannot just grow on like this, right? Then it will be disaster. Somewhere it has to stop. Any tree cannot just grow on. So that's why you can see. So that's why you can see some of the nodes, for example, node 2, node 12, 13, 14, and 30, 31. These 6 nodes are the terminal nodes. Okay, that means we are not dividing this, we are not splitting these nodes further to create any new nodes. So this is where the nodes are ending. We are not splitting it further. So these are called the terminal nodes. Now again, how we are deciding whether this is a terminal node or non-terminal node? Machine will decide it for you. Okay, so we don't have to take any pressure for that. Now, one more thing is, so this is how you create your tree. Okay, rather machine creates your tree. Now, of course, your model is trained, or your process is trained. Now, new observation you need to predict. That's the purpose, right? New observation you have to predict. So it's very easy. For that, all you have to do is you have to just place your new observation to the correct node. Okay, to the correct node. For example, suppose a new observation has come to you. You want to predict using this tree, and that new observation has ETA day as say weekend, then ETA shift between 1 to 7 say, and vector type as feeder. Then you go like this, and feeder. So this 127.90, this particular value, which is the average delay for this particular node, is your predicted delay for that new observation. Okay, that's all. So that's easy it is. So this is very easy technique and very useful because it's very easy to implement. Okay, this is also very old technique. I think most of you know already about it. So let's do one thing. So we'll come back to decision tree later. Let's now move on to the next paper. Okay, similar kind of paper, but only difference is in this paper, this Ernst paper, very recent paper, 2020 paper, they have used multimodal freight transport. So the paper that I just discussed, that paper used only transportation by vessel, right? There they used transportation by truck, and then by vessel, and then by train, from their warehouse to Bremen, Germany, to warehouse to Vance in Alabama. Okay, so that's their structure, and they had numerous of predictors or features. Okay, numerous of predictors or features. So what they did, they categorized their whole numerous set of predictors or features into different data according to different data sources. So for example, some of their features or predictors came from their tracking system. They had some tracking system. I'll not go into the detail of it. Then some of their predictors came from some of the predictors are country specific. So for example, country location, okay, derived from some geo coding API. Okay. Then some of the other predictors are day class. So for example, whether it is weekday or weekend or public holiday in that particular country or not. And the last kind of source is the clustering. So they divided the whole routes to different clusters. So that's why these are the 4 broad categories of features of the predictors they had. Now, just like last time, in the last paper, we were predicting delay, okay? But here we are predicting arrival time. So what is the predictor? What is the response or the variable that we want to predict? The variable that we want to predict is the one which is in bold. So time in hours from the current transmission to the destination. That's the variable we want to predict, right? And these are just a few examples of their whole list of predictor variables or the features. I mean, they have numerous. It's not possible to list down everything. Then I will need probably 50 slides, which is not meaningful. So I have just given few examples. For example, absolute distance to previous. So absolute distance in kilometers from the previous position to this position. That's one of their predictor or feature, which is coming from their TNT data source, that means tracking system. Similarly, departure day class. So whether it is weekday, weekend, and so on. So that's why that's how they have different features or predictors. Now, with all these numerous features and predictors, what they did is they did something like this. So primarily, let's look at the bottom of the slide. They applied these 3 machine learning technique, okay, support vector regression, extremely randomized trees, and adaptive boosting. Now, what are these? I'll discuss briefly all these 3. But interesting is, for all these 3 methods, since they had a lot of features, so for all these 3 methods, they applied these things for 42 possible cases. So how come 42? First thing is, they had, as I said, they had different kind of data sources, right? So they considered 3 different subsets of data sources. For example, this first yellow box is the features only coming from TNT, that means tracking system. Similarly, TNT, country, and day class features. And finally, all TNT, country, day class, and clustering. So that's why they have 3 different subsets of data sources or feature sources, okay? Now, for each of these 3 subsets of feature sources, they considered 14 possible ways of selecting features, which is on the top of the slide. So what are the 14 possible ways? So of course, I will not go into all the details, but the first thing is no selection at all. So they consider all features. That's one possible way. Then the second criteria is variance threshold. So how much variability the predictor has, okay? That's one of the selecting criteria, one of the feature selecting criteria. So likewise, they had 14 different ways of selecting features. That means of selecting predictors, okay? That's why 3 times 14, 42. So for each of these machine learning techniques, they had 42 possible cases, okay? Now, let's do one thing. Let's keep this paper aside for a moment, this N. Servo's paper 2020 for a moment, okay? And let's now first have a high-level discussion on some famous machine learning, state-of-the-art machine learning methods. Then again, we'll come back to this paper, okay? So the first thing is I would like to discuss is bagging. Again, I think some of you already know it. So what is bagging? Bagging, so decision tree and the card classification and regression tree we have already discussed, right, in the few slides back. Now, the idea of bagging is exactly in line with the idea of decision tree. The only difference is instead of just fitting one decision tree, here we'll fit multiple, okay? That's all. So we'll consider multiple random subset or using the bootstrap sample. By bootstrap sample, I mean taking sample with replacement from the same data. So we'll take multiple random subset from the original data and we'll just fit that decision tree for each of that subset of the data. That's all the concept. See, as in this picture, in machine learning, as you know, there are primarily two types of data: trained data and test data. Trained data means based on which part of data you train your model, And then once your model is trained, then based on this test set of the data, you check the performance of your trained model, right? So as you can see in this picture, this trained set, that means your trained data, is from this trained data, you sample you sample m times. So the first subsample is bag 1, the second subsample is bag 2, and the last subsample bag m. Okay, so all these bag 1, bag 2, bag m are coming from this train set data by doing bootstrap. Okay, now based on the bag 1, you fit your first decision tree right here, which is model 1. Similarly, based on bag 2, you fit your second decision tree, and finally based on bag m data, you fit your last decision tree, right? Now, all this model in machine learning, for example, decision trees, SVR, and so on, these have some parameters, okay? These are called hyperparameters, which needs to be fine-tuned, okay, for better performance. Machine will do it for you, don't worry. Now, for that purpose, for that fine-tuning purpose, you need to keep aside some part of the data. That's called validation set, okay? So train set is that part of the data based on which you fit or you train your model. Validation set is second part of the data, which is used to fine-tune those parameters. As you can see, the parameters of these models are being fine-tuned so that the performance becomes better and better. For that, we need this validation set. And so what's the last step? Once your model is trained, once the fine-tuning is done, then the last part is, of course, to check the accuracy of the model. And for that, you need the test set. So for the test set, you use the test set of the data, this part of the data. For example, say 30% of the data you use as test set, and you employ to everywhere. So for example, model 1, you fit model 1 based on this, model 2, model m, and your final prediction will come as the average prediction using all this model. So that's the concept of bagging, okay? So as you can see, concept-wise, it's very simple. It's just the decision tree, but you are parallelly training M decision tree or M model, right? You are parallelly training them. So that's bagging. Okay. Now, the next thing is, of course, very famous random forest. So the idea of random forest is again very similar to bagging. Okay, it's very similar to bagging. Just like that, I mean, we have here multiple trees, tree 1, tree 2, tree 3. But the only difference is in random forest, remember, in case of decision tree, this variable was chosen by machine out of all the 5 or 6 variables, right? Or all the features or all the predictor variables that you have. In case of random forest, the idea is a bit different. Instead of choosing this noding variable out of all the possible variables, you just choose it randomly from 2 or 3, from a subset of the all variables. Okay, you don't have to consider all the variables. You just choose a random subset, say 2 or 3 variables, and from that you choose this variable for each node. So that's called random forest. Okay. So one common sense is, again, this random forest is an theoretically this random forest is an improvement over this, the bagging or the decision tree. Why? Because firstly, it's an improvement over decision tree, right? Because in decision tree we are considering only one tree, right? But in random forest we are considering multiple decision tree. That means we are taking decision for more trees or from more models. So there is chance of lesser error. So that's why this random forest is theoretically better or an improvement over the usual decision tree. That's one difference. And the other difference is here while choosing these noding variables, we are not being very restrictive, right? We are choosing it randomly in this case, not we, the machine. The machine is choosing it randomly. So we are asking machine to become more flexible in terms of choosing this noding variable. So that's why, since it's more flexible, so that's one of the reasons this random forest is an improvement over the classical decision tree or the I don't know if it's working or not. Yeah, classical decision tree or the bagging. Okay, so that's the idea of random forest. Now, finally, one more improvement. So we have already seen the decision tree. From decision tree, you have one level of improvement to bagging, and then from bagging, one level of improvement to random forest, right? Now, there is one more level of improvement possible, and that is called extremely randomized tree. So this is a comparatively newer thing. So what is the main difference? The idea is again very similar. From random forest to extremely randomized tree, the key difference is, in case of random forest, we were choosing that cutoff to split the node optimally, right? The machine was doing some maths and machine was choosing that cutoff point optimally. But in case of extremely randomized tree, that cutoff point choosing is random. Okay, machine will not spend much time on this. Machine will not do any maths. So by cutoff point, I mean this. Okay, this arrow and this arrow. This splitting cutoff point. Earlier, in case of random forest, the machine was doing some maths. Here, the machine will choose it randomly. That means, in case of extremely randomized trees, we are adding more flexibility. So that's why it is further improvement over random forest. So we have a path of improvement. Path of improvement: decision tree, then bagging, then random forest, and then extremely. So am I audible? Yeah. Then extremely randomized tree. Okay. Now those all decision tree and random forest are done. Now just one more concept, that's called boosting. Okay. So in boosting we have again many different kinds of boosting, but I will just briefly discuss about two things. So the idea of boosting, in some sense, is similar to the idea of bagging. Okay. In bagging, if you remember, in bagging what we are doing, I'll just go back. In bagging, what we had multiple learner, right? Model 1, model 2, and model M. So multiple learner or multiple models we are doing. In boosting also, we are fitting multiple models. But in case of bagging, we were doing it parallelly. Okay, we are fitting all the models, or we are training all the models parallelly. In case of boosting, we'll do it one by one. So that's the key difference between bagging and boosting. Okay. So this is the idea of boosting, which is depicted in this picture, more specifically the adaptive boosting. What it does is, it basically, so in the first step, you fit or you train your first model, okay, or the classifier, say, and then of course it makes some error, right? If you are doing for the first time, if this is your first learner, it will make some error. For example, as you can see, these circle points, this and these two are the errors. Why? Because see, this plus is this is the classifier, right? This is the boundary between the two class, this dotted line, and this plus sign is wrongly classified with the negatives, right? So that's why this is an error, and similarly these two are also errors, right? So this has made some error, the first learner. Now what this learner will do, the first one will do, is it will warn the second learner about these things. So it will tell the second learner that, hey, I have difficulty in terms of dealing with these 3 points. So you better be watchful about these 3 points while you fit your model. Okay. So while you do the job, you be watchful about these 3 observations, and you put some extra weights on these observations so that you don't make the same mistake that I made. Okay, that I made. So that's why when the second learner fits the model, it puts some extra weight. See, that's why it's in bold, this, and this. It puts some extra weight on these 3 observations. And likewise, it goes on and goes on. So each learner, of course, fits the model, makes some error, but it warns the next learner about the error they had made. Okay, so that's the idea of adaptive boosting. And we go on. Of course, we cannot go on all the way. So ideally, we should go on till what? We should go on till there is no wrongly classified observation, right? That's the ideal scenario. But in practice, that doesn't happen always. Well, in practice, there is some kind of stopping criteria that machine uses. We can also provide some stopping criteria. And of course, this is the idea of adaptive boosting. Okay. That's what I have written over here. It pays more attention to the previously misclassified data points in the next iteration. That's the idea. Well, now the next step is what's called gradient boosting. So again, here the idea is similar, but here instead of just warning the next learner, what it does is the first learner fits the model. The first learner, that means this one, fits the model using x and y. Y is the response variable and x is the predictor. It fits the model, regression or classification, whatever be the case. And then it has some error, right? Observed minus fitted. It makes some error. Then what it says that, well, it tells the next learner that, hey, this is the error that I couldn't tackle. This is I cannot control. So you take it and you fit your model and see what more you can do. So the next learner use x and use the error that the first model made. See R1. So instead of x and y, it now fits the model based on x and R1. And it goes on like this. So here the idea is each time the first learner, okay, the first learner fits the model, makes some error, and that error is transferred as a response variable for the next learner. So that's the idea. One by one, this gradient boosting is doing, okay? And of course, there is again some stopping criteria. And there is one more version called XGBoost, which is a newer technique, but I'll not go into the detail of it. This uses some kind of regularization. Yeah, you can have a look later. So, okay, and finally, this is the last concept, machine learning concept. This is the last one, which is called SVR, or the support vector regression. So this is also a very famous technique. Of course, many mathematics are involved in between, but of course, I'll not do that here. So what's the idea? The idea is, in case of simple linear regression, what we do? We do a line fitting, right? So these are the observation, and we fit a line. We fit a line so that the distance between the points and this line is minimized. That much we all know. Now, the main difference between a classical simple linear regression and a support vector regression is this. Instead of fitting a single line, here we'll fit a plane, okay? We'll fit a plane, and this plane can be linear or can be nonlinear too. Here in the picture, it's linear, but it can be nonlinear too. We'll do it in such a way that this line is there, but there is an epsilon sensitive tube. That means we'll cover some more area in such a way that the distance between this point and this plane, see this, and then this and this, these are minimized, just like simple linear regression, vaguely speaking, okay? So why this is used? So this is used primarily for one of the very important reason. I'll just mention that the simple linear regression is not that useful if we have outlier in the data, okay? If we have many extreme observation, but this does bit of this does a better job in case of outlier, presence of outlier. So that's why, that's the primary reason it uses it, and it has other use as well. So well, so we have discussed about many things. Well, so let's just summarize what we have discussed. So we started with decision trees, right? We started with decision tree, the simple decision tree, classification and regression, then improvement, bagging, then one round of improvement, random forest, and then one round of improvement, extremely randomized trees. And then we considered different boosting methods: adaptive boosting, gradient boosting, and XGBoost. XGBoost I didn't discuss, but yeah, you can have a look. So, and also, what is the difference between bagging and decision tree? You have to remember it. In bagging, we fit the decision tree parallelly for multiple subset of the same data. And what is the difference between bagging and boosting? In bagging, we fit multiple models parallelly. In boosting, we fit multiple models one after another. They help each other. So that's the basic difference. Okay. Now, with all this very high-level idea of famous machine learning techniques, let's now go back to our paper that we're discussing. So what we had this N-Servo's paper, and they had multimodal freight transport idea, right? So they were predicting the arrival time, and they used this three techniques: support vector regression, which I have discussed, extremely randomized trees, and adaptive boosting. And for all these three methods, they considered this 42 possible ways of selecting features or the predictors. Okay. This is one of the famous way when you have too many features or too many predictors, and you don't want to use all of them because not all of them are meaningful. You have to somehow choose or select the suitable features. Okay, there are other feature selection criteria as well. I will discuss in my last slide. So what they found something like this. So they ran these three kinds of machine learning techniques, as I already mentioned, and they have reported, for each of these three, they have reported the best out of 42. So for extra trees, that means extremely randomized tree, this is the best scenario they got. So considering all the features and using this threshold using this criteria as a feature selection, these two MAE and RMSE are some kind of measure used in statistics, which is used to measure the error, okay, measure the accuracy, the error you are making for using this model. So see, this is the lowest they got for this extra tree. Similarly, for adaptive boosting, this particular combination is the best, because for this particular combination, these measures MAE and RMSE are the lowest. And for SVR, these are the lowest. And see the last column, this is also important. These are some parameters. See, remember I talked about fine-tuning of the hyperparameters. All these machine learning techniques have some parameters, actually many parameters. I also don't put all those things, but the machine knows, the machine does the job for us. So it selects the optimal parameters. You provide data, machine learns about it, okay? So that's why the machine has reported the best parameters. N estimators and random state are some hyperparameters for this particular algorithm, okay? One good thing is you don't have to do it. Machine will learn and machine will choose the best hyperparameter value for you based on your validation set. Okay, good. Now another work in the same flavor is by so what we did here actually. So what we did here, they considered it's very common practice, you know, when you have, so nowadays so many techniques are there, starting from decision tree, boosting, bagging, and many new techniques are coming into the pictures, coming into the market actually. So people gets confused, right? So it's good idea to run actually multiple, instead of just fitting decision tree, you run multiple things and you select whatever is best for you. That's the approach they have taken. And how you select based on that error value, MAE value or RMSE value, okay? So this paper did the same job, this Valesco's paper. They considered actually three response variables, this PC1, PC2, and PC3. These are the three variables they wanted to predict. What is PC1? PC1 is some time between order and departure. Similarly, PC2 is time between departure and estimated time. And PC3 is time difference between departure and actual delivery of the order. So these are the three things they wanted to predict. And just like the previous paper, they fitted multiple machine learning techniques, random forest, some boosting, bagging, gradient boosting, XG boost, and so on. And they choose the best one, okay, based on the RMSE value. So that's the idea. Okay. So yeah, this is one of the important things that I would like to mention. See, in the last few minutes, probably 15 or 20 minutes, we have discussed about many machine learning techniques, right? Many machine learning techniques. I mean, they have fancy name, bagging, boosting, support vector regression, XG boost. So just because these names sound fancy, it doesn't necessarily say that the performance will be better, okay? So we have to be very cautious while we use these machine learning techniques. So that's why this is a very famous phrase that we as a statistician use. So don't use a cannon to kill a mosquito. So you don't have to always employ very fancy tools and techniques, okay? Rather, my suggestion will be you start with simple linear regression, logistic regression, or simple classification problem. You try with that. And then if you want to use this machine learning techniques, you go one by one and check, okay? One of the thing is in this the machine learning techniques that I have discussed, sometimes it happens that they perform superbly with the trained data. That means based on the data based on which you are training your model. But while the new observation comes, that means the test data, they're disasters, right? So you have to be very careful. Just because they are performing well based on the trained data, that means based on which you have trained your model, it doesn't necessarily mean that if you change your data a bit, say 2-3 days later, then this model will perform same way, right? Rather, on the other hand, the simple techniques, simple linear regression, logistic regression, they are very much robust. Okay, they are very old technique. They are very much robust. Simple technique, more robust. So that's why, as you can see, I have given an example. This paper, this Alcoba and Holland paper, they were predicting again some on-time delivery of tracking industry, and they found a better performance by logistic regression over random forest and neural network. So logistic regression is simple logistic regression is doing better than random forest and neural network. So as a suggestion or for the practitioner that you start with the simple techniques first, and then you go to the further complicated tools and techniques. Okay. Now, so we have covered quite a few things. So actually, we started with arrival time prediction, and we discussed a few papers, and then we jumped back to some state of the art or famous machine learning techniques, and again we arrived here. Very quickly, I would like to discuss just 2-3 slides on demand forecasting. Okay, this is one of the other major problems in logistics and transportation. Now, before going to that paper, Jaipuria and Mahapatra paper, 2013 paper, I would like to focus on the second question or the second bullet point. The question: so what is the basic methodological difference between a prediction and a forecast problem? See, in case of arrival time prediction, what we had some x and we had one y, right? We were predicting y based on x. But in case of forecasting problem, usually the idea is a bit different. If you want to forecast something, that comes the temporal dependence. You have some past data on y, and you want to forecast the future y, right? So that's the basic difference. So that's why methodology-wise also there is some subtle differences, okay? And that's the reason to capture the temporal dependence, so the effect of past on future, to capture that kind of dependence, we usually use this kind of time series model, okay? For example, I have given one example here. This is AR model, autoregressive model. So y at this time point, that means t, depends on y at t-1, t-2, and t-p. So last year data, probably not last year, last time point data, two previous time points data, and p lag data. So that's how we kind of model this temporal dependence in statistics. And of course, it has some other variants, ARMA. We add few more terms, ARIMA, we take some differences here. So those are some other variants of this kind of model. Now, this is the traditional way. This is the traditional statistical way of doing things, autoregressive model, okay, or the other time series model. But the idea is it possible to improve the forecast given by ARIMA or the ARMA or the MA, the traditional time series model? The answer is yes. So this paper has showed that some advanced machine learning techniques, which is here DWT-ANN. I will discuss briefly what is DWT-ANN. Using this DWT-ANN technique, they have shown that they are getting better forecast, less error than this traditional statistical models, right? So that's why I'm saying. So in the previous slide, I mentioned that sometimes in the previous slide you saw, right? So here you saw that traditional tools, logistic regression, is doing better than fancy machine learning tools. And immediately on the next slide, you saw that the machine learning techniques are doing better than the traditional time series models. So if you ask me which is better, there is no answer. You can't have an answer. So you have to start with simpler thing. You have to implement fancier things one after another. So that's the usual way of doing things. Well, so again, now coming back to this paper, what was their motivation? Their motivation was accurate forecasting of demand, because it has direct effect. It has direct implication on this bullwhip effect or the net stock amplification. So it's very important to correctly forecast the demand. Okay, so that's their motivation. And of course, they were using the existing paper or the existing method were using the traditional statistical tools, that means time series model, but they came up and they used some fancy machine learning things, which is DWT-ANN, and they got the better result. So what is DWT-ANN? So its DWT is full form is discrete wavelet transform. Again, it has some maths involved in it. Of course, I'll not go into that detail. I'll rather go it visually. So this is what? This is this is the sales. So of course it's demand forecasting, right? So what is the most suitable variable? So sales. So this is the sales plot over different time points, right? Over different time points. So as you can see, what does DWT does? So discrete wavelet transformation, the name sounds fancy. What does it do is, it basically decomposes this whole time series into different parts. Okay, it decomposes it. So as you can see here, there is a trend. Okay, so trend means an increasing trend. See, from here it increases. So that's their approximation. That's the first part, approximation. And other than that, it has decomposed this whole thing into this 5 different components: 1, 2, 3, 4, 5. This is nothing but, these 6 things are nothing but some decomposition, some possible decomposition of this whole series. Okay. Now, why does it do so? The idea of doing so is, in the next slide, what it will do is, it will feed all this data, all this time series data, to your artificial neural network, ANN model. Now, if you feed this data, this complicated data, your ANN will be confused. Okay, it will become difficult for ANN to process this kind of difficult structure. Okay, your prediction accuracy will be less. So that's why instead of providing this kind of complicated data to feed your ANN, you rather decompose it into some simpler structure and then you provide it to ANN. Then your prediction accuracy will be higher. So that's the idea. So again, this is in this slide we have just I have just given you the architecture of the ANN. Again, some of you have already seen this picture many times. So for ANN, what's the structure? The structure is very simple. So we have some input layer. So it works just like our brain. Okay, it has some node, some neurons actually, and they're connected through different nodes. So, and of course, from this to this, some typical mathematical functions are involved. I'll not go into that detail. Actually, to be honest, it's not possible to know all the details. It's a black box kind of technique. So once you feed, the idea is simple. So once you feed the data into this, then it does something in between. These are called hidden layers, and then it provides you the output. So that's the classical structure of ANN. Okay. So using this structure, what we had. So as I said already, DWT plus ANN, which they have used, that paper, Jaipuri and Mohapatra paper, does the same thing. So they first take the whole time series data, sales figures, year-wise or time point-wise, I think quarter-wise, and then they insert it in DWT. They feed it in DWT, okay, and then they decompose that. This DWT decomposes the time series into different component. This A stands for approximation, the train, linear train that I showed you, that's the approximation. And then you have different detailed component, just like in this picture, the last 6 boxes. Okay. And then all these 6 things or 7 things goes to ANN. Now for ANN, it becomes easier because it is being fed with the simplest structure. Okay. And then ANN predicts the demand. So that's the structure, or that's the architecture of this DWT plus ANN. Now, of course, it has some mathematics involved. And the good thing is we don't have to bother about the mathematics. The machine will learn from the data and do the job for you. And ultimately, we are getting better forecast from the traditional time series model, which is good news. Okay. And yeah, here the results are actually there. So as you can see, as I already mentioned, see MSE, or the mean square error, it measures the error that you are making in terms of predicting the sales, right? So lower the MSE, better the value. So as you can see, traditional ARIMA models are doing worse, and DWT ANN methods is outperforming the traditional time series methods. Okay. So that's why, as you can see here, the machine learning technique, which is DWT ANN in this case, is performing better. Okay. Now, there is one more paper. The name of the paper, I don't think you can see it because it's blocked. But they have also this kind of methods is called hybrid modeling. Okay, because you are using multiple models. See there, you are using ANN, then DWT. You are using multiple techniques and clubbing together. That's why they're called hybrid model. Okay. This paper, this is also a very recent paper. They are also using this kind of hybrid modeling. Okay. So they start with the original time series. they first predict the linear trend, the trend that I showed you in the last paper, by traditional statistical time series model, which is SARIMA, some version of ARMA model. And then the remaining part, they feed into this machine learning techniques. Okay, they get the prediction out of this, all these three machine learning techniques. The first one is neural network. Okay, backpropagation neural network. This BP stands for backpropagation neural network, one variant of neural network. The second is we have discussed support vector regression. And the third thing we'll not discuss today, which is GP, genetic programming. So they feed the data in all these things, and they get three sets of prediction. Then again, they use something called GMDH to choose the optimal prediction. Okay, GMDH stands for Group Method for Data Handling. This is also very famous, getting very famous nowadays. So that's why they're using this kind of hybrid structure to improve their prediction. Okay, to improve their prediction. They could have used just the SARIMA. They could have used, but they tried using some machine learning techniques, both traditional way and machine learning way. They combined it. That's why this is called hybrid way of doing things. And they found that the prediction is getting better. Okay. Yeah, so this is the last slide, the summary slide. So I'll just summarize what we have discussed today. So firstly, of course, we started with the motivation, and not in only transportation and logistics. So in many fields, in pharma or in finance, everywhere machine learning are being useful. And that's why my nephew asked me that question, that should I ask ChatGPT or not? So you cannot avoid it. Okay, you have to deal with it. You have to learn about it, because that's the order of the day. And for today's discussion, we talked about arrival time forecasting, arrival time prediction and demand forecasting. These are the two topics we discussed. But of course, there are many other areas, as I already mentioned: industrial process optimization, then food delivery time prediction. That's also a current hot topic. Again, it has some further nuances. And then we roughly discussed almost, I'll not say everything, but almost all the state-of-the-art methods. Okay, these are traditional state-of-the-art methods, starting from decision tree, bagging, and then random forest, all the way up to GMDH. Now, there are many other methods, and people are inventing every day. Okay, they are combining one with other, and they are calling it a new method. Okay, you can also do that. But the idea is to understand, at least on a high level, all these things before applying it. So these are the tools that we have discussed. Now, the third point is important, as we have already mentioned. We need to be cautious. Okay, it's always better to start with a simpler approach. Okay, in the beginning, then you go to the next step and check if you're getting better forecast or not. But my suggestion, actually, the statistician's suggestion, is to start with the simpler one: the logistic regression, simple linear regression, simple classification, and so on. Okay. And then some other future directions that we haven't discussed today, but I have seen some of the papers have used it in transportation and logistics. These are called regularized methods. So regularized methods is nothing but, suppose you have many features. So one of the paper we saw, right, they had numerous features, and they use some feature selection techniques or feature selection criteria. So in regularized methods, what you do is you take everything, and then you nullify some of their effects. So that's regularized method. And then you can consider some spatiotemporal structure of the demand, or say any other variable, how it varies over different countries or different region of the country, and time-wise, quarter-wise. So that kind of problem you can consider. And sometimes we can have multi-dimensional data. For example, demand across different product categories and different age groups. So why only considering demand for only one product category? We can have different product categories and different age group. Then we have two-dimensional kind of data. We can go to the three-dimensional case as well. So these are some of the future direction, or the most recent direction in the research in transportation and logistics using AI and ML. So, well, yeah, this is all. And thank you. If you have any question, we can have it. Yes. Yeah. Yeah, yes. You are audible, but I don't think the online people can hear you. I think that's why you need a microphone.
Thank you for the wonderful talk. So I just need one clarification. I want to know, so you had mentioned while discussing the servos paper that random forest is better than bagging, or some of the other ML techniques are better than the other.
Theoretically, I mentioned the word theoretically, not practically. I mean, every data is different. Okay,
Right.
so for some of the data, this method can predict better for some of the other data. Yeah. Now, what's your question?
So was that in the only in the context of flexibility?
Yes. So yes, that was only in the context of flexibility, because in case of random, so what I said, random forest is better than the
Bagging.
Yes. So in case of bagging, that the choosing of variable based on which you're creating a node, so that was out of all the variables. But in random forest, that's just based on some subset of variables. So it takes less time, less complexity. It becomes easier for the machine to understand it. So that's why it should perform better way. But in practice, it does not always. So it will depend on your data.
So at the end of the day, we'll be only choosing the ML technique depending on the data set, right?
Yes, of course.
Okay.
Yes.
Thank you.
Professor, thanks a lot for the talk. Sorry, my throat is a little sore. I just want to ask you one question. We have seen the arrival time predictions. We've also seen the other techniques. But how does it help me in making decisions? Can you tell me about that?
Yes, of course. So making decisions means...
Yeah, what decisions, decision modeling, what type of decisions do I make? I know the forecasting, you have summarized it.
Right.
Now, you told me about the arrival time predictions.
Right.
What are the decisions it helps me in taking?
So, well, these methods helps in better forecasting or better prediction. But again, then, for example, I have given well, on the Nobel search, I think Professor Devjit Roy will be of more help in this case. But for example, let me go back here. Yeah. So, so just for an example, so we are predicting arrival of vessels, right? We're predicting arrival of vessels in the port, and it has some direct or indirect connection with many problems, like how much resources you need, how many workers you need, like how many containers you need, and all. So everything will depend on it, directly or indirectly. So it's always better to have greater accuracy, right? So that's the main idea. Even if a better accuracy will give you a very huge benefit.
Second question which I have, it is little to do with mathematics. Are these variables dependent or independent? When you make all these trees, X and Y, are they independent variables or dependent?
X and Y, you're saying?
Yeah,
or
in case you do decision modeling, first you need to have the independent variables. Similarly, when you're telling me the arrival time predictions, when you go from initial decision trees to the further bagging, and you have also used the variable slacks, which may be some error mechanism you must be using to correct the data sets. And finally, when we also come to that linear regression SVR initiation, you said you use a tube. Basically, it has got some slack variable errors on both sides. Are the same variable slacks or
well,
the slacks as well as that variable, what you called it in bagging something, you made a mention. There is some this thing.
Right. So yes.
Are these the same things? Because somehow I could not pick up that.
Well, there are subtle differences. So so in case of bagging, say,
can you go on to that slide? I will tell you
which one, the bagging?
Bagging one first.
Okay. It should be here. Yes.
You see this validation set. So I presume that this is some kind of given set of solutions within which you want to function.
No, these are not the set of solutions. These are just one chunk of your data. This is your whole data.
Yeah.
This is your whole data. You have just divided your whole data into 3 parts. Majority of them are trained set based on which you will fit your M models or whatever models, M learners. And then validation sets, this is the smallest part of your data, which you have kept aside.
What is it validating? If you say validation set, that must be having already.
This is just a name. The purpose, yes. The purpose is it's being used to fine-tune some of the parameters. Okay, so your initial part of the data has been already used to fit the models, and then it has some parameters.
I'll just try to further clarify, Professor. You use different models, model M1, M2, M. All these will be giving you different data. These data are dependent, interdependent, or not?
These data, they can have, theoretically they can have same data. Actually, you know, this bag 1 and bag 2 will have common data, because all of them are coming from this trained set based on bootstrap sampling. So random sample with replacement. So it may so happen that this one data set is present here, here, and say here. So there can be, of course, there are, so these are just the subset, random subset using bootstrap sample of the same data. So just you are feeding your M learner some subset of the data parallelly, and you're fitting the model or the training your model, and then you are collating all the predictions in the last step.
So in that case, if the error is not validated, how do we cater for that in the outcome?
Yes. So error is validated here, test set. See, using the test set of the data, the error you predict, you use your data, this part of the data, and you check how good your prediction is. Similarly, how good your prediction is here. And finally, how good your prediction is here. And then, well, I haven't mentioned it because I was trying to avoid the maths. So finally, this prediction, well, this average prediction is actually some weighted average, okay? So the weight will be higher for the weight will be the highest for the best performing model, and the lowest for the worst model, okay? While you take the average to calculate your final prediction, you do weighted average, okay? So that's where this performance will come into the picture.
Right now, can we go to the second one, SVR model?
Yes. Yes.
Here you see the right side graph. You are given as a set of error slack variables on both sides. So do we understand that the error is onto the positive side and the negative side? Why onto both sides of the mean?
Yeah, it can have both sides, right? I mean, for example, here we
understand that it's a mean distance, minimum distance, which you try to take from each variable. Now, why the error is on both sides of the mean?
On both sides of the mean.
Slack variable, which you have taken, it is on both sides. Why it is that?
So it can have both sides. I mean, why?
What is it helping me in understanding?
No, it's not helping you. I mean, these variables are just like one of those variables, right? I mean, some of them, see, we are not, instead of just fitting a line, we are fitting a plane. And that's why some of the variables, just like this, will stay outside of this plane, in both direction, both upside and downside. So
do I take it that it helps us in giving some clearance or some margin before we predict the outcome? Because when it comes to time prediction, it will have a lot of meaning. It
actually,
may not help much in delivery,
right.
but it will be important when you are predicting time.
So in case of time prediction,
slack variable is doubled, you see.
Right.
When I take the tube condition, slack variable is doubled.
Right.
Because you're using sigma on both sides.
Okay.
So should I take only sigma or 2 sigma or whatever is that variable you have put?
Yeah, no, that's a good question. But well, first thing is I haven't used it. They have used it, so that's why I have posted it here. But yeah, as you have correctly said, there will be two slack variables will be doubled. But well, I mean, it can have something like that. We can have it something like this. But yeah, it's a good thing to have a look. Yeah. Yeah. Q&A. Okay.
So let me read it out to you. Yeah. So the first question is, how to select a model out of many techniques? Should focus be given on flexibility or accuracy? What is your opinion in this complex business environment?
So yeah, as I have already mentioned, you know, there is a very nice graph. Unfortunately, it's not here in terms of flexibility and accuracy. You know, what I would suggest is start with the simpler one. Okay. Of course, if you fit very complicated model, for example, bagging, boosting, and so on, it will use your it will use your trained data very well. Like it will overuse actually the trained data, and it will give you a nice model for the trained data. But when new data arrives, it may perform very badly. Okay, so that's why my suggestion will be you just go with the simpler one. You just start with the simpler one, and then you go on, increase the complexity.
So the next question is how to implement these techniques in our daily work.
That's a very general question. So of course, well, I showed you a slide. So why, when, and what, this you have to decide, and for how you have ChatGPT. So you ask ChatGPT, ChatGPT will write the code for you, and of course you have to make sure that the code is correct. So there's Python open resource and R open resource. So you just type. So once you decide the method, getting the code or getting it implemented is not a problem nowadays.
So moving on to the next question, it is on what basis do we select the subsets of features from which the parting node is to be selected in a random forest model?
Yes. So for a random forest model, on what basis we select the, yes, so that's a good question. So that I avoided. So actually that is done based on some mathematics. So it chooses that variable, based on which, and that variable and that splitting cutoff, based on which there is maximal homogeneity. Okay, so what's the ultimate goal? The ultimate goal is to create two different groups out of one group, right? Two different groups or nodes out of one group. So you want this node and this node to be as much different as possible, right? Otherwise, what's the purpose of making two different nodes or making two different groups? So there is some mathematical formula involved. You can just go on to any machine learning book, but that's the basic idea. So the two subnodes you are creating out of one node, one main node, the parent node, those two subnodes should have to be like as much different in terms of their features, okay, as possible. So that's the idea.
So we have one more here. When we are starting with the data, just by looking at the data type of attributes of the data, do we have any tricks to tell which method might work better?
Actually, you can do some EDA. EDA means exploratory data analysis, what the statisticians usually do, but it's not possible to say correctly. Okay, just by looking at the data and doing it some random check, it's not possible. Of course, you have to look at whether there are outlier presents in the data and so on. But again, my suggestion will be the same. You start with the simpler one, check the prediction accuracy, and then you move to the fancier ones.
Thank you, sir. Next question is, in bagging, how to identify the ideal ratio between training set, validation set, and test set?
Yeah, so the ideal thing is probably training set is at least 70%, and then the rest of the 10% for validation set and 20%, so that's the usual norm, 20% for the remaining test set.
Next we have, can ChatGPT help me how to select the appropriate model for a particular problem?
No, unfortunately not. ChatGPT cannot. So if you decide the model, then ChatGPT will tell you how to write the code for it. There is no way.
Next we have, sir, how do we check the accuracy of the prediction?
Accuracy of the prediction. So accuracy of the prediction is very easy to check. So there are RMSE, root mean square error, just some square difference between the prediction and the actual. So that's RMSE value. So you can just check the definition of RMSE. I have showed in the slides as well. So that's the usual way. And we can, instead of square, we can check also mean absolute error. So these are the two standard way. So lower the RMSE, better is the prediction.
So we have a question from Pramod Kelkar. He wants to know, is there any practical example or company where this is being used, maybe a pharma or discrete manufacturing?
Company that I don't know, that probably Professor Devjit Roy. Okay, you know? Yeah. Yes.
Actually, I worked at Tracker. We had a client where So we had a client there where actually I worked for the route optimization problem, basically the traveling salesman problem, where you are actually optimizing the routes of the salesperson who are visiting the dealers.
Right.
And so that was a part of it. And there's also demand forecasting that we did for another CPG or FMCG client, where we were predicting the demand. That was a US-based client. So yeah, these are practical applications of this.
Great. Thank you.
Thank you, sir. Next, we have, sir, in today's world, we collect huge amount of data. Sometimes it is high dimensional. Does all this ML techniques fit well in these scenarios?
Yes. These ML techniques fit well in the scenario. So high dimensional data can have problem if you fit the simple linear regression. There you need some lasso and that kind of regularization. But these ML techniques can handle any dimension.
Thank you, sir. So we have a question here. In regression, we have p-values. What we have here in these models?
See, here we don't need the concept of p-values, right? Here the idea is prediction, okay? If you are using these ML techniques, if you are training your model, and the ultimate goal in this case, so p-value is what? P-value is you are checking the significance of your coefficient, right, beta, and checking the significance of your ANOVA or anything like that. Here the idea is different. The idea is to get greater accuracy. So p-value is irrelevant in this case. You need that RMSE, root mean square error, because prediction or forecasting is the key thing here.
Next
Otherwise,
question.
like p-value, you will get the p-value here as well. So if you have like m different learner, if you fit m different simple linear regression, then you will get the p-value here for some of the models. But p-value we don't actually need in this case.
So next question we have here is, do the data have any particular characteristics to apply a particular machine learning technique?
No, I don't think so. At least I don't know. You have to go with the simpler one and then the fancier ones. Yeah.
Moving on to the next question. Yes. No, you can ask the question. What are the most recent advancements in machine learning and data science within the transportation and logistics industry? How have these advancements impacted operational efficiency and cost reduction?
Okay, so I think this is the same question you asked. So how it has impacted the operational efficiency and cost reduction, I don't know that in detail, very detailed, because I haven't worked on that part. But the first part of the question, what are the most recent advancements? These are the most recent advancements, because this is the most recent reviews of the papers that are there in the market. So, well, yeah, these are the techniques.
So one last question, which machine learning algorithms are most commonly used in transportation and logistics applications?
Again, my answer will be this one. These are the machine learning techniques that are mostly used. So I would say decision tree and SVR, bagging boosting slightly, as I think you have used. So these are the tools. I mean, there are some fancier tools, some newer tools, but mostly this. Yeah.
So that covers most of the questions from our online participants. So
final questions. Really impressive ones. Okay, if not, let's thank the speaker again. Just want to add a few things over here. I think Professor Samrat mentioned several methods, both in demand forecasting and also in time and arrival prediction and all. We can anticipate so many applications, right? Whether it is food deliveries or your Swiggy deliveries, Instamart. In every case, you're given a time. So how do you really predict it accurately matters a lot, not just for your customer experience, but also for the backend part of it, right? So once you're given a time, how do you really ensure you achieve that? So that's where you were saying, right? So you get what are decisions, right? What are the decisions? So once the estimate is given, how do you plan backwards towards it? And that's where a lot of work has to go in as well. And there are a lot of examples. I think opportunities are limitless. For example, we have been working a lot with Flipkart and other companies, and we see so many applications. They have dedicated data science teams who are working day and night for pricing, for markdown optimization. You can think about the inventory optimization. Where do you keep the inventories? You can think about what should be the price the seller should put on the platform, the recommendation engine. Today, the whole things are using AI/ML in some form or the other. So I think this is just a tip of the iceberg, I would say, right? There's a lot of things going on. And as you mentioned, every day, new method is evolving and finding its own application. So I think this is a very ripe field. And if you're interested to work in this field, I think this is the best opportunity to step in. So thank you again,
Thank-
Professor Samrat Roy, for making, and thank you all for coming at 6 p.m. in the evening. I know evenings are for other things, but you found a better reason to be here. So thank you again for joining us.
Thanks. Thank you
And
so much.
yeah, we have a small memento for our guest speaker here.
Oh.
So thank you again.
Thank you so
for this
much.
massive talk. It's very nice. Welcome to this. Thank you. And stay tuned.
Oh.
Okay.
Thank you.
And stay tuned for the CPL updates. We have many more things lined up for this particular term. So stay tuned and reach out. So thank you again for joining. And I want to thank you. Thank you.
Thank you.